Okay, good morning. Good morning. Hold up. Okay, so today we talk about random numbers. And we want to produce random numbers from a given distribution, especially given PDF function, which is the probability density function, probability density function, which tells me what is the distribution of a variable. It is a way of telling me its distribution. And the second thing that we want to do is to to find an integral or to make multidimensional integration numerically using random variable or random producing of numbers. So, and it will be a better way for us in multidimensional integrations, a better way when the dimension grows, when the dimension is high. So at first we'll talk about producing random numbers. We'll talk about three ways of producing these random numbers. The first way is the inversion way. It is a successful way. It's a good way of producing numbers, but it assumes that we know the PDF function and we know how to integrate it and find a closed formula for it. And after that integration, when we get the cumulative distribution function, we know how to find the inverse function of it if it is invertible. And after that, we'll talk about the acceptance rejection method. And after that, we will combine these two methods in some hybrid method. And this has its own advantages, of course. So you know that in the real world, in the real, let's say like this, there's no real way using a classical computer, but the computer we have, there's no real way using the classical computer to produce real or really random numbers. So we somehow produce pseudo random numbers, and we assume that we accept the fact that a given computer can produce for us a uniform random, a uniformly sample variables or numbers from 0 to 1. That's something that we will assume. How it does that? So it takes some seed, some number, and make for it many manipulations, and eventually it looks like, or it appears as if it came from that distribution that we want. But we will not talk about this. We will assume that the computer knows how to produce these uniform numbers from 0 to 1. And our goal is to know how to use them in order to produce random numbers from another distribution, not uniformly from 0 to 1. And in order to make a numerical integration in some new method, which is called the Monte Carlo method. So I know that you took a course of probability, and this is a reminder for you in the appendix. If you forgot something, this appendix, I think it's enough for you. And I will remind you also of the important things, I think, They are important. So you remember that the probability space is a triple of omega, f, and p, where omega is the sample space and f is the events field, which is the set of all subsets of this omega, and p is a function from p to 0, 1 to the segment of 0 to 1, which is called the probability function, and it has to meet three axioms, which are these. Okay. Every function p that meets these three conditions is a probability function. Okay. So for the same omega and f, I can produce many probability functions. And when we have a probability function, we can use it to define another probability function, which are called conditional probability functions. So if we go with this definition of P of B given A is P of B and A divided by P of N, we can prove that this new function, which I can call PA like this. So this is a new function. I can prove that this new function is also a probability function that meets the three axioms of the probability function. Conditioned, or if I know that P is a probability. Okay, so that these things you've done before. And another important thing I want you to remember or to recall that random variables are functions of omega. Okay, so this is the space of all outcomes that I can get from some experiment. Let's say this is the physical space, and for each omega in this omega, I assign a number in the real axis. Okay, and I can assign another number. I can use any method I want. Okay. For example, for a dice, you can tell me the outcome. That's the number. And you can tell me the square root of that outcome. That's another number. Okay. So it is a function of the outcome. So when we say x, it is x of omega, and we drop that omega because we understand that it is x of omega, which is in this omega. Okay. For example, if I have an electromagnetic experiment and I have something in the physical real world, these are the outcomes, and this is a statistical experiment, let's say. So I can assign for each outcome in the physical world its electrical field in the x direction at some point. Okay, so that's the number I want to ask about. Okay, so I have a physical world, and my random variable is the electric field at some point in the direction of x. I can ask about the electric field in the direction of y. That's another random variable. Okay. Is it sufficient for me to know the variable in order to know the outcome itself? No. This is an example. If I tell you what's the electric field of it, do you know the real outcome in the physical world? No, because you have to tell me also EY and EZ and BX and BY and BZ, and maybe you have to tell me what's the temperature. Okay, this function does not have to be inverted. Okay? And of course, I can tell you many numbers. Okay, and put them like this. So this is not a random variable, it's a random vector. Okay, so for each omega, in this omega, I assign a vector in R to the set. Again, I can ask about another thing. For example, I can ask not about these. I can now ask about the let's call it T. I can ask about the energy or the electromagnetic energy at some point, which is E squared plus D squared over 8 pi. And maybe there is a closed form or a known function that can connect between x and y, and maybe there is not. Okay. For example, here we have a connection between this variable and this random vector. Okay. Again, I'm talking about some random experiments. So these are random and this is random also. But this u is this squared plus this squared over 8 pi. Okay. So I have a function from x to y. So sometimes I have a function. That's a good thing to know. Sometimes I have a function between x and y. Okay. Questions? Okay. So we define the cumulative function of the random variable x at a point x to be what?
P of x.
Yes, we don't define it as the integral. We define it as the probability of x being smaller than or not bigger than. And we define this to be the derivative of it. Okay. So I want you to remember all the time that fx is a name of a function. Okay? And fx is a name of and fx at some point x. This is not a name of a function, it's a variable. It's the differentiation with respect to that variable of fx at that variable. So basically I can write down, for example, fx of y squared. Okay. I can write something like this, and it is the differentiation with respect to y squared of fx of y squared. Okay. So fx and fx are the names of the function. Okay. And of course, we can have a continuous random variable and discrete random variable and a mixed random variable, which have part of it discrete and a part of it continuous. For example, the amount of rain today. Okay, so there is some probability that there will not be any rain. So it's the probability for 0, and after that we have a continuous density of the probability. Now we want to ask, if I know this function, can I know what is fy if I know what is fx? So the answer is yes, in many cases. And fy at a point y is, if I know what are the x's that are suitable to that y using g. So I want to know which x's solve this equation. And if I know that this equation, its solutions are xi goes from 1 to infinity, so I assume that this equation has a finite number of solutions or a countable number of solutions. And at each point of these, the derivative of g is not 0, I can say that fy of y is fx at xi divided by that at xi. Okay, so for example, if I know that y equals x squared, it's like this. Okay. Or for example, let's talk about a particle in one dimension, its velocity and its kinetic energy. Okay, so it's squared. If y equals x squared, then if y at some point y, of course y is positive, and let's assume that x is a continuous variable, random variable. So let's ask, what are the x's that solve this equation? So this is g of x. G of x equals x squared.
Why do you want to solve this equation? What one?
I told you a theorem, and I want to use it. The theorem says the density function of y at some point is the density, the sum of the density function at the points that solve g of x divided by sum. So what are the solutions here? Plus minus, yeah, plus minus. So x plus minus equal plus minus. These are the solutions. And what is g tag or g prime of x? G times 2 times x. So what is g prime at these points? And what is the absolute value of x? It's the absolute value of this. So for both of them, the answer is 2 square root of y. And therefore, the answer here is fx at the first one divided by, and fx at the second one divided by. So if you know the density function of x and y equals x squared, the density function of y is this. First, I assume that x is continuous.
You play in like
That's the two here.
okay, there's the derivative, right?
Okay. So what is this proof? Why is this proof? Suppose that there is one answer, okay? Suppose that g of x is invertible in the domain that x is defined at, and suppose that always you have one answer. For example, e to the x, it has one answer. Okay. Why is this true?
Maybe Chingwood? Chingwood?
Somehow, yeah. So first we can, first of all, prove it. Okay. We can prove it. How to prove it? We calculate the probability of y being between y and delta y. where this delta y is the delta y of some delta x. So when we take delta x and delta y to be 0, they are the dividing between them is the, the derivative, and we can prove this. Okay, it's not hard, but I want you to see the proof in another way. You can call it you can call it the, the conservation of probability. Yeah. So it has to be that the probability of f of x dx over some region, it has to be equal to g of that a, the image of this a, fy of y dy. Why is this? Because when we say f(x) of x, for example, p of x less than x, what's the meaning of it? What's the meaning of this definition? F(x) of x is the probability of x being smaller than x. What's the meaning of this? This x is x over omega. I know what is p defined on f. So I know that my probability space is omega f and p, and this p is defined on f, the set of all subsets of omega. So what's p of x smaller than? I know that p is defined on this, not on this. What's the meaning of this? It means the probability of omega being in the set of all omegas that meet the condition that x of omega is smaller than x. That's the meaning of that function. Okay? Okay? So if I have some event that I describe it with this, I have some event here. It corresponds to some event here, and it corresponds to some event here. So if I take some region here, which is called A, that A, and integrate over that region, and I take the image of A using G, and I integrate over this region, it's the probability of the same event. Okay? By definition. All of you understand this? No. Okay. So suppose that I have something here called A prime. Using X, it's a bunch of events here, a bunch of outcomes, all of them, I take them as a set. It's a continuous set here. If X is continuous, I take all of them using X, and I know that this omega goes to this number, this omega goes to this number. All of these are numbers. Okay. And the same thing, I take it here. Okay. Now, if I integrate over fx over fx in this region, I have to get the probability of this event. Yes? And if I integrate, so this, let's call it ax. This a, and this, let's call it ay. And it has to be that ay is the image of ax using g. Because both of them describe the same event. You can suppose that this function is invertible, So we know you can compose functions. Okay? You can compose functions. Y of something here, or let's say this thing, if I have some y here and some x here and some omega here, I know that omega equals x minus 1 of x, and it equals y minus 1 of y. Okay. So I have this connection between x and y. Okay. So both of these integrals describe the same describe the probability of the same event, so they have to be equal.
Shouldn't be zero AM.
What?
Shouldn't be
Yeah.
AM.
Yeah.
Thank you.
Okay. So because they have to be equal for every a, then using the change of variables, I can prove that Fy is this. Okay, it's only a change of variables of integration. Again, you can see it through this. If you don't want, you can see, or you can check the proof using differentiation, not integration. Any questions?
Can you explain again the line rating in the red? In the omega equation?
Here?
Yeah.
So this is if x is invertible, so the inverse function of x is omega. Because x of omega is
Okay.
oh, so that's what I wanted to say. And of course, if the function is not invertible, we have to go back to the definition in order to solve. Okay, so it's not invertible, or I'm talking about this G. If I don't have a countable number of solutions, or if G prime is 0, so I have to go back to definition in order to solve. I cannot use this theorem. Again, this theorem is only a conservation of probability. That's what you called it before, I think. And now we are physicists. Up to now we were mathematicians, and now we're physicists. So we'll not use fx of x and fx of x. We will say p of x dx equals p of y dy, and we will in absolute values, and we will, it's a convention between us here in this lab, that when we say p of x, we mean by that fx of x. But when we see py, we mean by that another function, which is fy of y. Okay? So it's not a correct notation, but if all of us understand this, okay, we can use it. So what's written here, for example, is also here conditioned, or yes, if it's there is only one solution, so this is the same. And this absolute value, you know why? Why is this absolute value here? It's because of this, of course, but why is it? Why do we have to use this absolute? Because the probability is positive, and maybe if x increases, y decreases, yes? Okay. So what's our inversion method? Our inversion method is to produce, if I want to produce x Okay, now let's read this. If I want to produce X, that its distribution described by some PDF, I want to produce X, and its distribution is described by some PDF. And this PDF, I can compute for it. Its integral, which is the cumulative distribution function. And this function, I also know how to find the inversion of it, the inverse function of it, if it's inverted. So I assume three things here. That I can integrate over fx and find a closed formula. Then the second is that f, capital F, is invertible in some domain that I want to ask about. And this inverse function, I can write down as a closed formula. Okay. If I know all these, I can take a number, u, which is distributed uniformly from 0 to 1, and then apply on it, define x to be the function, the inverse function of that. You know what? Ignore this. Okay, I produce this u, and then apply for it the function fx minus 1 and get fx minus 1 of u. And I claim that if you do this, this thing, which is a function of u, is distributed as you want it. Okay. Now don't forget that this is a function. Okay. Of course, it's some function which is which corresponds to a probability thing. Okay, but it's a function. So this is the density function. It's also a function. I calculate from it a function, which is a cumulative function of x. Okay, but it's a function. And find from it another function. It's a function. So the g here is the function fx minus 1. Okay, that's my g.
It's not d minus 1.
It's g. No, it's g. Because I took u, I applied upon it. What is this? Okay, I produced a random number u and calculated for it fx minus 1 of u. Okay, that number is distributed as we wanted, and that's it. You got your trial or your sample. Yeah.
What?
Huh?
That u equal that.
I don't want to say equals. I want to say distributes like this. And now I have to prove for you that it distributes like this. So I want to prove for you that this thing that you got distributes like X. I want to prove for you that the probability of it being smaller than some X is what? What do I want to prove for you?
That x is 1.
I want to prove that this is fx of x. Yes? Okay. So I know that this function is, suppose that x is continuous, and I know that this function, if it's invertible, I know that fx is what? Monotonic and increasing. Yeah, if it's an increasing function, monotonic. Yeah, that's why it's invertible. So if it is a monotonic function that all the time increases, the probability of this smaller than this is the probability of fx applied on this smaller than fx applied on this. Okay, if I have an increasing function, x is smaller than y, if and only f of x is smaller than f of y, if it's an increasing function. So apply f here, it's the same even. The probability of f of x, fx applied on this is what? Fx of x minus 1 is the argument itself, it's u, smaller than fx of x. Okay? Now this thing is a number between what and what? By definition.
0 and 1.
Between 0 and 1. And the u is a random variable uniformly 0 and 1. So the probability for u to be smaller than alpha, if alpha is between 0 and 1, is what? Is alpha. Yes? So the probability of u being smaller than this is this. Okay? So that's it. So this thing that we produced distribute like x. So that's a sample of what I wanted. It's a sample of that distribution. Okay.
Can you explain again that
The last step. This is a number. Okay, call it alpha. But I know that this alpha is between 0 and 1. The probability of u smaller than half is half. The probability of u smaller than quarter is quarter. Because u is a uniform variable between 0 and 1. Okay. And I want you to try to prove this, not in this way, but using the theorem. So I leave this for you. Using the theorem, I want you to find that f for this thing, call it y, fy for y. I want you to continue using the theorem and prove that it's what? Using the theorem that we wrote before. If we want to find, call this y, and I want you to use the theorem that we wrote about y being g of something. This is u here. I want you to prove that fy of y using the theorem is what?
fx over y side?
Y. Fx of y. That's what you have to prove. Because that means that this thing that you produce has a PDF like the fx. The density function of it at some point is the density function of x at that point. Okay? Okay. So that's a graph that shows what we say. Suppose that this is the function, the given PDF function. I calculate for that PDF the CDF, the cumulative distribution function. After that, I produce U uniformly between 0 and 1. for that u, I go to the function and find the inverse function of that. So that's the value that I take for sampling x. Okay. Questions? Okay. So here's an example for, okay, so here's the Rayleigh random variable, Rayleigh random variable, I can get it from example, if we have x and y independent variables, and x and both of them are distributed normally with 0 and sigma squared, so the square root of x squared and plus y squared is distributed like this, Rayleigh distribution. So it goes from 0 to infinity. And if we want to produce numbers from this distribution, we calculate the CDF of that function, and this is an integrable function, and we can find the closed formula of it because this x dx is the derivative of x squared up to half. So this integral is solvable. And we can find the the inverse function. So we can take -1 and then multiply by minus, and then take the natural log and then multiply by -2 sigma squared, and then take the square root. So that's the answer, but there is the square root is missing here. So we have to multiply by square root of 2. And we can also check the ends of the distribution of the variable itself, because u between 0 and 1 has to take me to x between 0 and infinity. X can take values as large as we want. Yes, it goes to infinity. So for u equals 1, we have 0, and for u equals for u equals 0, we have the log of 1, so it's 0, and for u equals 1, that's the right end, we have to get infinity. So for u equals 1, this log is very, very, for u equals 1, but you get to 1 from below. Okay, so this is a very, very, very small number. Okay, and then we have here infinity. Okay, because this minus we can take it here, so it is we can take it here for a power. So we will have the log of very, very large number, which is very large, square root. Okay, it goes to infinity. Yeah.
What is u again?
What is u? U is the produced number, which is uniformly distributed between 0 and 1. And we apply on that number f minus 1. Okay. Question?
How do we call you?
You produce it from the computer.
So how we get from the fx to yu?
That's our method. Our method to produce u, to perform for it fx minus 1.
How we produce u?
The computer knows how to produce u. That's our assumption from the first. We assume that the computer knows how to produce uniform random between 0 and 1.
The equation behind the y 1, but we got infinity. Why it makes
What's the intuition of this?
Yeah, but not like mathematically.
Yeah, so the intuition, because I use this number, plug it for it a continuously decreasing function, And I have to get all values of x because I proved for you that I get the density function of x. So I get all values of x that x can have. Also, their density function is like the density function of x. The last x has to be the last u. Okay. Another example, for example, here f of x is a this multiplied by this exponent between 1 and 2, and outside this region it's 0. So what's this a? What's this a? It's a normalizing factor. It's a normalizing or normalization factor, which is 1 over the integral over this function in the region. Okay, so it has to be that the integral over this from 1 to 2 equals 1, and then I find a. Okay. After this, I have to find capital F and then take the inversion of it. And again, that's the function that I use. Okay, so I produce u, I enter this u to this function. The number I will get is a number that is taken from the distribution that I want. Okay. And here is the graphs of p, for example, and f. Not important, but this is important. So if I take my way and produce u, find f minus 1 of u, that is x, and write down that x. It's x1. And another sample, u2, and find x2, which is the fx minus 1 of that u2. And then u3, and then u4. And I do 50,000 samplings like this, and find the 50,000 x's, and I build a histogram of these x's. This is what this histogram will look like, and it's not p of x here, it's p of x multiplied by 50,000. Yeah? So we get a very, very good approximation of what we wanted. And using the central limit theorem, we expect that if this number goes to infinity, the histogram, if the histogram of also we took it smaller, and so it will go to the function tab. Okay. Questions? Took us time. So now we'll talk about another way, which is the acceptance or rejection method. Suppose that fx, which is the PDF, suppose that that we have it, or we have it from, for example, interpolation or some data. Suppose that we have it, but we don't know how to integrate over it, or that its integral is a complex function or complicated, or that its inverse, it is complicated, we cannot find that inverse. Okay. So how can we deal with this? There's the method of acceptance and rejection, and it is a very, very easy method. It says like this: you have a distribution function, example, between A and B. That's your distribution function, P of X. You can bound it by a box or by a rectangular. Now, I don't have another. You have? Thank you. Yeah.
It's about time for a break. So
Yes, I know. But 5 minutes?
no, you can go get a new marker.
Hmm?
You can go get a marker.
No, 5 minutes. Okay. So our method is to produce many pairs of xi and yi independently. I produce these x's uniformly from A to B, so the computer knows how to produce them, and I produce these y's uniformly from 0 to this maximal value, to m. So m is the maximal value of this field. Okay. So I produce many pairs. Okay. Part of them will be here, but also part of them will be here. Okay. For every pair that have a yi that is bigger than p of the xi in that pair, I drop the pair itself. So I drop all these points. Okay. I don't accept them. And the points that I accept, I take the x's of them. The y's are not relevant for me anymore. And these x's that I got are distributed as I want them. Okay. So I described this using many points, but it's also true for one. If you take 1 point, xi, yi, and you take this, and if the yi is bigger than p of xi, you drop it, then the x is distributed as you want it. But we have to prove it. Okay. But if I use it for many points, you somehow see it. Okay. We didn't prove it yet, but that's the way, or that's the method. We will prove it after that, today. Okay. So that's my method. Okay, the x's that are left are distributed as I wanted. So for example, here is a function. So what can I do? I can produce many points. The computer knows how to produce them, and only if for each point that the yi is bigger than the p of that xi in that pair, I drop it. And of course, the efficiency of this, the accepted points, the number of accepted points divided by the number of all points I have sampled, is what? Is this region divided by this region, by the whole region, the rectangular region. Okay, the area. So here, for example, if you calculate the efficiency, it's that this area divided by the whole area, it's 75%. And it's so clear for you. And here is an example. Okay. So again, I sampled many points, and then kept the xi's that I kept, and then built a histogram. And of course, 50,000 is better than 5,000. And you already see that if this function is somehow narrow in the region, so the efficiency will be very small. Okay? The efficiency will be very small. So we can think about a way, or think of a way that we combine the two methods that we found, the inversion method and the rejection or acceptance rejection method, and we'll talk about it after the break. We will prove it also, and that method contains this method. This is a special case of the method that we will do. But we have to start with this and then go to that and for our differential. So now let's go to a break for 10 minutes. Okay. Now we have a hybrid method that combines between the inversion one and the acceptance and rejection one. And it is good, for example, for a function that is like this. So that's A, that's B. And you see that this, you know what? That's the function. And you see that if I want to take a rectangular here, the efficiency will be so low. Okay. Yeah. So I try to bound this function with a function, another function that I know how to integrate over it and to find a closed formula and to find this closed formula is invertible and to find the inverse function. That's this function. Okay. Another example, for example, here we have a function that goes like this. And instead of this rectangular, I find a function that I know how to integrate over it.
But it's very close.
It has to be at each point, at every point, has to be above the function. Okay? So this function is P of x. This is P of x. And this function cannot, the red one, cannot be a density, a PDF of some variable. Why?
Because it's bigger than.
Yes, because the area under it is more than one. But it can be some C multiplied by. Okay. Questions? Again, this function now, if I know how to get from it, f, which is invertible, and I can find the inverse. Okay? Okay. Now, we produce U from a uniform distribution. The computer knows how to do this. And we produce X from this distribution. How do we produce X from this distribution? Using the inversion method. Okay. So I produce I produce many samples of it. Okay. And now I will accept pairs and reject pairs. If U 0 multiplied, or ui, let's call them ui, multiplied by c, multiplied by f of the xi is bigger than p of the xi, and ui are from the same pair. If this happens, I drop that pair. Okay. I produce many pairs, and if this happens, I drop that pair.
Why?
Hmm?
Why?
You will see that we will get the same, we will get the distribution we want. And we will prove that. Again, I think you've seen the motivation here, and you can think somehow about this and find the same motivation from, like the motivation here, you can find the same motivation, but you have to think a little bit more in order to write down this. But at first we write it down from the motivation and then prove it. It's like many things in mathematics. Yes.
What is the meaning of C?
C is some number that using it, the C multiplied by F will be above it.
Yeah, we can just call it some with G of X.
Huh?
Why you want to call it G of X instead of C minus X?
You want for me to call this G of X? In order to make the difference between the part of this multiplication that its integral is 1 and the part which is not. Okay? And it is so important for me for that to be a multiplicative factor multiplied by some function which its integral is 1, in order for me to build from this function which is invertible, and these functions are probability functions, and I can produce random variables of them. Okay, and this C, you see it here. Okay. Now, why is this a special case of this?
Because this is from
What's the F here?
1 over B minus A.
Yes. So the F here, Fx here is 1 over B minus A. And what is the C?
Here, left node here, left.
So I know that C multiplied by F is the maximal value. Okay, so the C is by B minus A multiplied by F. Okay. So this is a special case of it. And you can see that if we write this here, it's the same thing. It's the same rejection condition that we use, because we, instead of U being between 0 and n, here U is between 0 and 1, but it will be multiplied. So it's the same rejection condition. And now we will prove that this gives me what I want. So the probability of X that I accepted is smaller than X is the probability of some, so this is an X that I accepted. So it's the probability of some X that I produced with some U, okay? Some X that I produced with some U, given that I accepted that. Okay. So I will be left with X's that I accepted them. What's the probability of X that I accepted it? to be smaller than x is the probability of the x that I got from my producing of the pair x and u. It's the probability of x to be smaller than x that I and accept it. Okay. So when we accept a point, we are left with x and drop the u. It's like here. When we accepted a pair, the y's are not important and the x's are my samplings. And here also, when I accept a pair, the u is not important and the x is my sampling. So when do I accept x? That's one. Okay, I accept x if this condition is met. The opposite condition. Okay. And now this is a conditional probability. So by definition, it's this. And x0 and u0, it's u0 here, u0 here. X0 and u0 are independent. So why cannot I say that the probability is the multiplication of the product between two probabilities?
Can you repeat the question?
X0 and u0 are independent. So why cannot I say that this is the multiplication of the product between the two probabilities? Because okay, they are independent, but we have x0 here and we have x0 here. Okay, so if you have, for example, x and y that are independent, and you want p of x being smaller than some x and y being smaller than x squared, it's not the multiplication between them. Okay, because for each x tag that x equals to, I can say that this is the multiplication, but I have x here and I have x here. So how to compute this? We'll calculate this. How to calculate this?
Official p of x smaller than x plus p of y smaller than x squared minus p of y.
No. Yes, summation. Yes, summation over the x's, which is integration over the x. So this is the integral over every x for this thing. The same thing, given that x equals x prime, fx of x prime. Okay. And now when x is equal to x prime, now I can say here x prime, and the probability is the multiplication. Okay.
What's the difference in
Again, you'll see now. So that's what we say. And now these are numbers, not random variables. These are numbers. And the probability of x here we have x0, but the x0 equals x0. Okay, so we have this probability, and the integration is from minus infinity to infinity. And now what's the probability of this event of x0 being smaller than x? They're both numbers.
x.
If x0 is smaller than x, this probability is 1. If not, it's 0. Okay. Okay. So let's take the same example. So this is x tag smaller than x, and y smaller than x prime squared. Okay? Now, given x is equal x prime, and I wrote this, I can drop this condition. And what's the probability of x prime? So this is the probability of x prime x smaller than x multiplied by the probability of y smaller than x prime squared. Okay? What's this probability? 1 if x prime is smaller than x, and 0 if x prime is bigger than it. Therefore, the integration here goes to x, and that's it. We are left with dx prime p of y smaller than x prime squared fx of x prime. Okay. The integral from minus infinity to infinity is the integral from minus infinity to x plus the integral from x to infinity. And the integral from x to infinity is 0 because this is 0 there. And the first one, this equals to 1 there. Well, we are left with only this. So let me continue. We have then the integration from minus infinity to x over this probability. And this probability, because u is uniform, so the probability of u being smaller than alpha is the alpha itself. So that's it. And this f cancel out with this f. And we are left with the integration over p and this multiplicative factor outside. Okay? And all of this is only this. Now, what's the probability of u being smaller than this, i.e. without this condition? If I don't have this condition, the integration here goes not until x, it goes to infinity. And the integration up to infinity of this is what? 1. And we are left with 1 over c. So this divided by 1 over c is this integral. And then, therefore, we prove that p of x smaller than x is this integral, which is f of x of x. Okay, so using this method of rejection, we are left with x that is distributed with the distribution that we want. Okay. And here is an example. This is a function that it's very hard for me to find for it the antiderivative or the cumulative function, and then to find the inverse function. Okay, you see that it's exponent multiplied by sine to the 4th. Okay, so what do? I take this function that bounds it and produce a random variable from this. How do I produce random variable from this distribution? Using the inversion method, and produce any ui. Okay, I produce the first u0, let's say, or u1, and produce x1. The u1 is uniform. The x1 is what? The x1, I produce some uniform and apply upon it x minus 1 of this function. Okay. And you can see that this is our rectangular way or acceptance rejection way. And this is our hybrid way, which is the acceptance rejection, but not with a box or rectangular, with another function that we produce for its random variables. Okay, here the function that we produced for its random variables was the uniform function. Okay. Here it's another function. It's better. So you can see that the efficiency here is better than the efficiency here. Okay, it's 40% compared with 25%.
How can you find the function that bound?
There's no algorithm for that. I can, for example, here the function is this exponent multiplied by sign. So you know that it is bounded by the exponent itself. That's an example. Okay. And if there is a function that I don't know, but I can draw some function which is above it, and I know how to integrate, that's a way. There's no algorithm for me to find that function. And the difference between the functions that I choose is only the efficiency. It's only the efficiency. So the difference between this function, which was the uniform function, and this function, which is the exponential function, is only with the efficiency of the process, because here I produce points in all this region, and here I produce points only in this region. The points that are produced are in this region, and I reject from them the points above P of it. Okay. Any questions? Okay. Now we're talking about another topic. After we know how to produce random variables, it's not really, it doesn't really depend on what we talk about now, because we will use now only uniform variables. So, but in the context of randomness, we can use a method which is called the Monte Carlo method of integration that uses random variables. Okay. So our methods are good. Trapezoidal methods, some methods are good. But when we have multidimensional integration, they're not so good. Okay. Why? Because, for example, in 3 dimensions, if I want to perform an integral over this region, x, y, z, I have to divide, or to make segmentation here in x axis, I have to make segmentation y axis, and segmentation in x axis, and segmentation in z axis. Okay, let's say that each one of them, I make the segmentation with n segments, small n. So the number of small cubes that I will use, this is a small cube, this is a small cube. The number of small cubes that I will use is n squared, because here I will evaluate the function of xi, yj, zk, where I, j, k go independently or run independently from 1 to n. Okay. So as you see, the number of points that I will take goes with the number in each axis to the power of to the power of the dimension that I use or want to integrate on. And if I am talking only about a 3D particle, a particle in 3D, and I want for some reason to integrate over the phase space, it's a space of how many dimensions? 6. I will integrate dx, dy, dz, dpx, dpy, dpz. Okay. So that's the problem that we are growing up with the number of points that we will have to use, and we will compare it with the Monte Carlo in a minute. But let's talk about the Monte Carlo. The Monte Carlo says, I sample these endpoints. If you want to sample endpoints, so the trapezoidal method for integration says that if you want to sample endpoints, these endpoints, you have to take the third root of them in each axis, for example, okay? And make the segmentation. In the Monte Carlo method, we say, no, these endpoints, I sample them here in this region. So I sample xi, yi, zi n times. The xi goes from here to here, the xi from here to here, the yi from here to here, uniformly, and the zi from here to here, uniformly. And I sample n points like this. And then I only find the average of the function over these evaluations of the function at these points. Okay. So why is this true? Let's see why is this true. Let's go to one axis. And I have a function. And I want to find the integral over this function. Okay. From A to B. Okay. So suppose that I have a uniform. Suppose that I have X, which is a uniform variable from A to B. And I'm asking you, what is the expectation of X? What's the expectation of X?
Between
A plus B over 2. Yeah? The expectation of X, if it's uniformly distributed. And what is the expectation of f of X?
Average.
Hmm?
Average of the function.
Yeah. So it is the integral of f of X dx 1 over b minus. Okay. Now, if I sample many X like this, and find the average of this sum. Let's say xi. I goes from 1 to n. Xi is the I sampling from. So I produce many variables independent of this or many samples. Okay. So you learn that this, if n goes to infinity, this goes to this, but we have to correct this sentence. This goes to this. Is this true? With probability 1. You remember that? No. You don't remember the central limit theorem and probability course? Okay. So this thing, if n goes to infinity, goes to that value with probability 1. Okay. So does probability 1 means certainty? Is it certain? Are you sure that it will go? No, but it goes with probability 1. And fortunately, somehow probability theory works in the physical world. Okay, some miracle. You know that if I say that the coin has half and half probabilities, it doesn't mean that if I make 1 million trial, I will get half and half. I might get the 1 million trial as heads. Okay. So probability somehow doesn't mean anything except being shocked with the physical world if it doesn't matter somehow. Okay, but we know that it works, and if I take many points, it goes to this. And I also know that the difference between this and this is, which is the variance, it is the standard deviation. It's also something that you prove. So we can prove it here in this. Okay. So now I know that the function, the integral over the function, is b minus a, the averaging over the function when I take many points. Okay. And if it's a multidimensional integration, the integral over the function over some volume, it's the volume, not the length, the volume multiplied by the averaging of the function. And if the function, if I take many points, it's better. Okay. And my error. So again, the integral is v. It's the volume multiplied by the averaging of the function when I take many points. And my error is, or goes like 1 over the square root of n. And that's the important thing. That my error goes like 1 over the square root of n. For any integration, for any dimension, it's 1 over the square root of n. So now let's compare. For example, if I want to use the trapezoidal method, let's say I want to sample 64 points. So I can sample for this problem. If I want to sample 64 points, I have to sample here 4 in this axis, 4 in this axis, 4 in this axis. Not sample. Here I have to make this segmentation. Okay. And therefore H here is let's say that this is L, this is L, this is L. Okay. It is L over N. It's 4 here. And this N is what? Is the square, the D square of N. Okay. And the trapezoidal method tells me that we converge the order of the error goes like this H squared. Okay. So it goes like n to minus 2. Okay. Questions? Yes, if I want to use the trapezoidal method. If I decided that I want to use n points, the trapezoidal method says to me that for this integration, that's your error.
And square root of n is better than that. And square root of n better than that.
Now we will say that. Now, if d is 4, the square root is like this. And if d is 6, for example, which is better? The square root. Okay. So this is called also the curse of of dimensionality,
But if
would
the
say,
pixel is one, for example,
then we will use not Monte Carlo for that. But now we can say that for any method of for any segmentation rule or any numerical integration rule or method that you will choose, you will have some critical dimension above which the Monte Carlo method will win. Yes.
What is it again?
D, the dimension, here the D is 3, the dimension of the integral that we are performing. We'll try to calculate. Okay, so again, Monte Carlo method is a method of numerical integration, but we're using it a random trial or samplings of uniform variables. Okay. Now, if the region that I want to integrate over is not this, it is, for example, this region. So it's somehow like the rejection method. Okay, so I can, if the function is g, I want to integrate, I want to perform the integral of g of x b3x, for example, over some region which is called v. That's the region v. So I can bound it, for example, by a box and define the function f to be g if the point is in that region and 0 if it's not, and then calculate the integral of f multiplied by calculate the integral of f using this. Okay, and again it equals 0 if we are outside the v that we asked about. So this is vs, for example. This is vs. This is vs, and the box is called v. Okay. And you can, for example, use this method to calculate the volume of some rigid body or its mass if it has density, mass density, some mass density, and you can calculate also the center of mass, and you'll have these in your homework. Okay. Any questions? Okay, so here we can say you can see it's an example of generating random numbers. Okay, so all what is important here that you can use this random and produce uniformly random variables. And if you know how to produce a random variable between 0 and 1, if I want it between A and B, I only use linear transformation, and then I will get what I want. Any questions? Okay, so that's it for today.